I copied this file over here, and then I'm looking at readme.tau. Now I may be going a little slow over here, so there are commands here to instrument your source code if you would like. So you can try that as well. But in this readme.tau, it says, first of all, use this source command, then untar the NAS parallel benchmark, and then go and do the make suite. First run it with the uninstrumented case, and then just change this run.sh to add the tau exec-ebs. That's all we'll do right now, and run it again. Everyone with me so far? We are building the uninstrumented binary, running it, and just changing the job submission script. So we say tau exec-ebs. Okay? So let's do that. Again, this was the README file in case you want to copy it. Okay, you can just cut and paste these commands on the terminal window. Just a show of hands, is anyone here not able to access the file, or you have problems connecting to the FX10 system? Everyone is okay? Okay, so let's try this. I'll build it and go to npb 3.3 mzmpi. First I'll say make clean, and then make suite. Here it will build the BT benchmark. We have not touched the build system in any way. Here we are just building the full executable, and let's just run this and evaluate the overhead. You should remember that whenever you use performance evaluation tools, there will definitely be a dilation in the runtime. Your code may run slower, but we want to balance the accuracy of the performance data generated with the volume of data that's generated. Okay? We want to reduce the overhead so that our instrumentation is coarse-grained enough that it can show us some insights in the inner workings of your code, but balance the instrumentation so that its overhead can be controlled. Okay? So here we see it built the BT benchmark in the bin directory. Can everyone see this? Built executable bin BT. So I go here, and there is my file. Now, just as I had written in the README file, I will copy from the job script fx10 the run.sh file over here. So step 1, build the application. Step 2, copy the run file. Step 3, launch the job like this. Now this is pretty simple, is it not? We have just taken a tarball, we have just typed make, created a binary, we have launched the binary using the pjsub command. Okay? Note that I have in my bash RC this command at the bottom. In my bash RC, you can see the source setup.sh. Everyone should have this. In your bash RC file, please add this source setup.sh to this path. Next, let's look at the output of the execution. Here is the output. It ran 32 threads on the FX10 system. You can see the time steps, and at the end, you will see the verification was successful, and it took 16.60 seconds. Now let's keep that figure in mind as we look at other options, okay? Let me turn on the run.sh and say just tau exec first. That's the only change I made. I just added the tau exec keyword and pj sub run.sh. Now here, I'm not doing the event-based sampling. I'm just measuring the time spent in all the MPI calls by just saying tau exec, plain. And I can see that it is executing. It's over. Okay. If I say seconds, do you see the difference in the runtime? It took longer. The original code executed in how much? 16.60. The code with tau exec took 16.69 seconds. Okay, you can see the dilation right there. But it does produce profile files, and I can launch paraprof and view the profile files. Okay, here I can click on this node and see the time spent in all the MPI calls, including MPI init thread and barrier and so on. Let's make it more interesting by changing the run.sh and adding the event-based sampling parameter to this. Okay? So note, the original line was this, and I added just that, tau exec-ebs. Now I say pj, remove the profile files, pj sub run.sh, and we run it this time with event-based sampling turned on. Again, no changes to your source code, no changes to your makefile, no changes to your binary. We are just launching the same executable with the tau exec-ebs. Okay? And now I can look at the output. You see, it took longer this time with the event-based sampling. The first experiment was at 16.60 seconds. The second experiment was 16.69 with the tau exec. And now tau exec-ebs dilated it from 16.60 to 16.70 seconds. Okay? But what can this show me? I can launch paraprof and I look at the right click a given, say, show me the thread statistics table. Now here is the thread statistics table. I can look at all of these nodes, MPI ranks, and right click to pick this. Right click over here, not here, not on the colors, but over here where it says nodes. I click here and I get this thread statistics table where I see the time spent in all the MPI calls. The time spent in MPI barrier, I see the time spent in the rest of the application. And I can open this key like this. And I can see within this there are functions. it shows me which functions are interesting. Now I can just sort them by the time spent in them by clicking on this exclusive time. And it says that, well, there is a function called bin VCRHS. There is a function called ysolve, zsolve, and xsolve. Okay? There is a function called matmul sub, and it shows me the time. It's taking about 5 seconds over there in the first one. It's taking about 2.3 seconds to 2.0 seconds in the solve functions, all of them. And then 1.5 seconds for the matmul sub and compute RHS. So that's a pretty interesting set of performance metrics there, right? You can see exactly how much time was spent in which function. But there is more. If you just click on this key, you can actually see where the sample was taken. So here, let me just move this, and I see the line numbers. Okay? I see the line numbers right here. And it says at line number 393 seconds, I received 27 samples out of the 890 samples that I got in this full bin VCRHS function. Okay? These are all samples, the number of calls. And I can just right-click on it and say, show me the source code which you think is interesting. And that's the code where it received the samples in that subroutine. You can look at other codes. You can say, look at the ysolve and say, show source code. And here is the code which is very interesting for the ysolve subroutine. Do you see that there's a triply nested do loop? And that line where it does the assignment is where it spent most of that time. So you can just jump straight to the line of your code with no changes of any kind. You just go straight to the statement and see that it took so many seconds in this line of code. This is an interesting region of code for your application. Okay? So, go ahead. Any questions? Yes? Source view? The first one. This one. So I just right-click over here on node 0. And then I click on thread statistics table. Show the thread statistics table just like I had in my slide here. So I launch Paraprof. To get this view, I am clicking on node 0. You can click on any node, right? And just say, show me the thread statistics table. Click on the column to sort. Open the keys on the left to expand. And get this view. So, yes, right click. That's why I use a real mouse instead of, or I have my corner of my, little trackpad configured to be the right mouse button. If you need any help with the Mac, just go to System Preferences and click on the trackpad and say the secondary click in the right corner to then pick that. So here, thread statistics table, open up the Tau application, and for instance, look at the xsolve. Take this, right click, show source code location, and jump straight to the source code right here in the OMP do loop over here. So I'm going to show a number of different ways to instrument your program, but I wanted to start this session with the simplest tool. Okay? What can we do with the simple tools and then move on to more complex workflows where we'll actually change the name of the compilers and generate the profile files. Okay? But this shows me xsolve, ysolve, and zsolve are the three main routines where they're doing the computation. And you can see the contribution of each of those statements by clicking on a given thread. So I'll just wait for everyone to just catch up. The steps are all there in this readme.tau file. I put this in my bashrc file, tar it up, go through this, run it, then change this mpi exec command to tau exec-ebs and run the program, launch paraprof after this, and then you can generate the profile files. Now, if you have any problems with the X windows and you can't display it, you can download our tools and install it on your Windows or your Mac system from tau.uoregon.edu, and then you can just pack up the profile files, so you don't have to transfer 20 files. You can just transfer a single PPK file or packed profile file to your desktop and then launch the paraprof to view it. If you're on a Windows machine, you can just double click on it, it will launch it. And then we can go to the source code instrumentation. Those of you who have finished the first part can go on to the next part. But just raise your hands if you have been able to use the tau exec-ebs and generate profile files. Okay. And are you able to launch paraprof and view the contents? And right click on it, see the source code, and so I'll just wait. Does anyone need any additional instructions for doing this? Does it look okay to be able to first try this? And those who have done this can follow along and go to the next part of source code instrumentation. You just have to cut and paste the commands that are in this file, and you'll be able to do the source instrumentation instead. If you do the instrumentation of your binary, then you don't need to launch it with tau exec. Okay, you can just launch it with your regular run command. Yes.
I don't see. I have lots of the windows of things.
Just open it up. Open up the tau applications. Open that up, and
Just all windows of. And I follow those steps.
are you running a smaller problem?
No.
BT bin? So one of the reasons you may get unresolved symbols is because your make file does not have a -G to resolve the symbols. So look at your F flags in the config make.def and add a -G flag. That does not preclude the instrumentation, but it will allow you to add the symbol information. Anyone else? Are you able to run? Yes? Yes, you can also do it like that, where you, instead of launching it remotely, if you have problems with X, you could just install tau locally on your laptop and then launch paraprof on your laptop and not worry about any X Windows calls. Yes, Peter?
I tried to launch PowerPoint on my local computer,
Yes.
but you can find source files.
That is correct. You will need to transfer the source file to some directory, and then if it says that I can't find it, you will have to go and click add a directory, a top level directory, where it can recursively search for the sources, and then you'll be able to see the source code. You are right. When we create the packed profile files, for obvious reasons, we don't include the source code in it, just the performance data in it. So you are... We cannot. We don't want to. Oh, so you do a right click and then say show source file, and then it will say I couldn't find it. So then you have to click the add button and then go to the directory and then hit close, and then it will come up automatically. But that's only if you're using it locally. We recommend that you use it over there right now, because you'll need to install Java on your machine and so on for the 3D graphics to work. So with this, is everyone able to do the first exercise and do tau exec-EBS? Do you need some more time for this? Do you have any comments about whether this is difficult or something to apply to your tools? Does it look okay? We just changed the run script and added that and run it. The next step is we will try to instrument the source code using our tau compiler scripts. Okay? So what I will do is I will take each source file, I will parse it, I will find out where the source code is located, at what source line, in which file. Within the routines, I'll identify the loops. I will instrument using Opari, the OpenMP constructs, and then link it all in to create the binary. This is a more involved process, right? And to do that, I will simply do two things. The first step is I will set the tau makefile environment variable that points to this Opari configuration of tau, and then I will change the name of the compiler. Okay? So follow along with me. Here, I cut and paste this line, echo $tau. I know my tau directory is over here because I use the setup.sh, and then I can just say export tau makefile to that directory. Okay? Next, I can say make clean. I'm not in the right place. Make clean. And next, I will say make MPI F77 equals tau F77.sh suite. Just like the README file, you can cut and paste this. All you're doing here is you're substituting a compiler with another compiler. You're saying, instead of using MPI FX FRTPX as the compiler, I'm going to use tau F77.sh. You could have said tau F90.sh or tau CXX.sh for C++ and so on. This shell script will read the tau makefile environment variable. It will find out the location of the directories the location of the MPI library, and link it in like this. It's instrumenting the source code, it's parsing it, it's creating the PDB file from PDT, and then it is going to instrument it and compile the instrumented code with the OpenMP constructs and generate the executable. While doing it, our build system is geared up so that it keeps this in separate directories. So instead of the bin directory, we're going to look at the bin.tau directory next. Okay, just like the README file does. Okay. Here you can see the detailed instrumentation that's taking place in the source code, and you create the object files. Everyone with me so far? Can everyone just cut and paste those commands from the README file and instrument the code? Okay. Now it's completely instrumented, and now I go to the, here you see it says build executable bin.tau. So let me go to bin.tau and copy over from the job script directory fx10 the run.sh over here. I will launch this with pjsub run.sh. That's it. So note what I did here. I set an environment variable. That's very important. Tau makefile. It picks up the configuration that I want to use, which has OpenMP and MPI. The second thing I did is I said make, but use MPI f77 equals tau f77.sh. But I did not edit the makefile. I did not touch the build system in any way. I did not touch the source code. But I got an instrumented binary at the end of this. Now I have run this, and I will run paraprof over here.